So this last chapter that we're going to cover is dealing with nuclear chemistry. So far, all of the chemistry that we have been looking at takes place because of the electrons and the movement of electrons, whether that is in the process of forming a solid precipitate, and then we used KSP to do that, whether it was the movement of these atoms so that their electrons would match up in the reaction of an acid base, or any other kind of regular kind of chemistry. We are looking at the movement of electrons or molecules or atoms or ions so that things will get to a lower energy point because of where the electrons reside. Nuclear chemistry, an entirely different story. We are no longer looking at the electrons, but rather what is happening in the nucleus. And so I want to start by taking a look at the things in the nucleus. Obviously, the nucleus is where the protons and neutrons reside. This is where all of the mass, for the most part, resides in an atom. The electrons make up all the space, but the protons and neutrons make up all the mass. And to illustrate this point, if the nucleus were a golf ball, the surface of the atom would be 1.5 miles away. So you get a feel for how big an atom is and how small that nucleus is. In terms of the mass, if the nucleus was the mass of a baseball, the electrons would be the mass of a grain of rice. And so again, you can kind of get a feel for how heavy that nuclear mass is. To illustrate this even to a greater extent, when I take a look at the density of the nucleus, and by that I mean how many grams per cubic centimeter there are, we have a difficult time, I think, imagining how much mass would fit into maybe a cubic centimeter. But now let's think about a cubic foot. So 1 foot by 1 foot by 1 foot. How much mass would have to be in there to equal the mass, or rather the density of a nucleus? And you would have to put in, excuse me, 6.2 times 10 to the ninth, or 6.2 trillion automobiles, put all of their mass into a 1 cubic foot sized space, and that would be equal then to the density of a nucleus. It's a very difficult thing to imagine, but true nonetheless. This takes us to binding energy, and in order to calculate a binding energy, we kind of need to know the masses of all these different particles. And so here you can see how heavy a proton or neutron are compared to that of an electron. These are atomic mass units, and so you can see the electron is very small compared to that of a proton and a neutron. Neutrons are just a little bit heavier than a proton. If you were to take an oxygen-16 nucleus, so that means you've got 8 protons and 8 neutrons. The 8 down on the bottom part of that oxygen, right over here, right? That 8 indicates the atomic number, and then the 16 above that indicates the atomic number plus however many neutrons there are in that nuclide. Right, so we've got 8 protons, 8 neutrons. So I've taken the mass of 8 protons and 8 neutrons and added those up, and we should get a mass of 16.132 AMUs for an oxygen nucleus. But as it turns out, the actual mass of the atomic nucleus is only 15.9956 AMUs. So we have a mass defect of 0.136 AMUs. If I subtract those two numbers, I get 0.136 AMUs. And if we use Einstein's general theory of relativity, which says that the energy is equal to the mass times the speed of light squared, you would end up getting an energy for this of 127 mega electron volts. Probably doesn't mean a whole lot to you at this point in time, but 127 mega electron volts is equal to 2.03 times 10 to the negative 11 joules. Well, that does not seem like a whole lot of energy, but think about that. That is for a single nucleus of oxygen, right? If you wanted a mole of oxygen, then we would have to multiply this number by 6.02 times 10 to the 23rd. And if you did that, you would get 1.22 times 10 to the 10th kilojoules per mole of oxygen 16. 10 to the 10th kilojoules. Typically, when we were doing the combustion of a mole of methane gas, so methane plus oxygen, so a lot more mass than just 16 grams, but a mole of oxygen, a mole of methane being combusted gave us about 800 kilojoules, so 8 times 10 to the 2. Now we're talking about 1 times 10 to the 10th, so significantly more energy tied up in creating this this nucleus for an entire mole of oxygen.